Hydrogen halides can also add on to alkyne, and they again follow very similar mechanistic rules as those observed for alkene. So if we have an alkyne which is internal, then it will add the molecule of HX. In this case, we cannot expect any selectivity, so we will get the mixture of two regioisomers pretty much always. However, if we don't deal with the internal alkyne, but instead we deal with the terminal alkyne, then Markovnikov rule will follow, and we will get exclusively the product which adds hydrogen to the atom that already had more hydrogen. Okay? We can often add the second molecule of HX, and in those cases, the second molecule is typically added in the same orientation as the first one. So if we have terminal alkynes, then we will end up with something like this. So geminal dihalide. However, even if we had an internal alkyne, we will get a mixture of this and this. But each one of these will now add a second molecule according to Markovnikov's rule. In other words, the orientation repeats itself in the second addition. Finally, one more detail about the addition of HBr is that the same rule that applied for alkenes applies here. If we use HBr with radical sources, then we will get anti-Markovnikov addition. So we'll add bromine to the less substituted side of the triple bond, and this will be now a mixture of V and Z. But the point here is that this will follow the anti-Markovnikov addition. As you can see, hydrogenation, addition of halogens, and addition of hydrogen halides very closely followed the rules observed for alkenes, with the notable difference that there was some intricacy added by the possibility of the second addition. But in this case, the reaction that we're going to discuss next, that is hydration, shows really a significant difference and mechanistic difference between alkenes and alkynes. So we'll spend some more time on it. And this will be the topic of our next subsection.